the course when we talked about respiration, we talked about the cardiovascular system, we talked about the urinary system. Each time we said, and acid-base balance is a function. So we need to spend some time just talking about acid-base balance. Our normal blood pH is 7.4, slightly basic. We can only withstand relatively small changes from that 7.4. We can go down to a 6.8 or up to an 8.0. But at those extremes, you have about 1 minute to live. So it's critical that our acid-base balance is kept intact, right? That we maintain the correct pH. So what is an acid? We learned at the beginning of the course, and you knew from chemistry, that an acid is a chemical that donates hydrogen ion when placed in water. For example, hydrochloric acid. What's a base? A chemical that accepts hydrogen ion when placed in water. For instance, something like sodium hydroxide. pH stands for potential hydrogen, and the equation for figuring out pH is it's the negative log of the hydrogen ion concentration. Okay? It's the negative log of the hydrogen ion concentration. Those of you in lab, you've been down this route before, but let's look at that just for a minute. So if we had a concentration of hydrogen ion that was 10 to the 0 power molar, what's 10 to the 0?
1.
1, right? So if we follow our equation that pH equals the negative log of the hydrogen ion concentration, we have to take the log of 10 to the 0, which is 0, and it says the negative log, well, minus 0 is just 0, right? So the pH of this solution, a 1 molar solution, would be a pH of 0. If, on the other hand, we had a solution that was 1 times 10 to the minus 14th concentration of hydrogen ion, and we wanted to take the negative log of 10 to the minus 14, well, the log of 10 to the minus 14 would be minus 14, but it says we need the negative log of that, and so that would mean our pH was 14. So the pH scale is 0 to 14. Midway is 7, which is neutral. And a very high pH then means a very low hydrogen ion concentration. A very low pH means a very high hydrogen ion concentration, which is kind of confusing, right? Because the scale is kind of backwards. You think, oh, more hydrogen, oh, that should be a higher pH. No, more hydrogen is a lower pH. Jessica? You know, it could, but beyond those, you're at an area that it's so small that it doesn't need to be measured. But you can get, you can have pHs, molar concentrations of hydrogen greater than 1 molar, right? And so you can have negative pHs, but typically in any kind of normal range that you're doing, it's 0 to 14. Yes?
Sorry, you said that the 1 molar solution was 10
to the 0, right? Because 10 to the 0, and so that's a 0 pH.
So it's a 0 pH, but what's the 10? It's just
base 10. So we're at the base 10. So if we take 10, so a log is the exponent to which you're raising. If we're doing base 10, well, you could do base 2, but that's not how pH was set up.
Okay.
Right? And so using a base 10, the exponent here is a 0, which means then 10 to the 0 is 1.
Okay.
Well, we keep our pH so tightly controlled, it needs to be so tightly controlled, that we consider you to be abnormal with your pH if you get a pH of 7.35 or lower, so 0.05 of a pH unit low, that we call that acidosis, or if you're at pH 7.45 or above, we call that alkalosis, right? So more than 0.05 of a pH unit up or down, we consider you to be in acidosis or alkalosis. So what mechanisms do we have for maintaining our pH so tightly?